Hi, this is the third video I've done on trigonometric substitution for integral calculus. And we've already done substituting a sine of theta and substituting a tangent of theta, just to remind ourselves. When you're integrating something that has something in the square root that you can put in the form of a squared minus x squared, strangely enough, you can substitute in a sine of theta for x and work it out. Similarly, when you have something in the form of the square root of a squared plus x squared, if you substitute a tangent of theta for x, you can often work it out. Well, this third video has to do with where you have something in the form of the square root of x squared minus a squared. Notice this is different from a sine of theta. With a sine of theta, you have the constant squared minus the variable squared. But when you have the variable squared minus the constant squared, then by substituting in a secant of theta, a lot of times you can work it out. And as a case in point, let's go ahead and do this one. The integral of dx over x squared minus a squared. This is the most basic form. By the way, because we're not using actual numbers, we are actually going to work out a formula. Now, I think for most of us, we don't memorize a lot of these formulas. There are often tables in the back of the calculus book. In fact, I'm following James Stewart's 6th edition, although his essential calculus also has much of the same material. Like in the essential calculus and also in his 6th edition, in the very back of the book, you have these formulas where you can look it up. There are some that you should just memorize. This is not one of them, I don't think. But being able to work out the formulas, that is, knowing the way, if you may not remember the formula, but if you remember how to reconstruct the formula, you're okay. Well, we're gonna construct one of the formulas here. What if you have the integral of dx over the square root of x squared minus a squared? Well, we're going to substitute in a secant theta for x squared, and let's see what happens. All right, let's go. So this is the problem we're starting with. Let's go ahead and substitute in a secant of theta for x. Right, and so what is dx then? Because we've got to substitute for dx as well. We're substituting a secant of theta for x. What then is dx? Well, the derivative of the secant of x is secant, or the derivative of the secant of theta is secant theta tangent theta. This is one that's kind of on the edge of my memory. I think it's one that I should have memorized, but it's also one that I can look up fairly easily, at least when I'm not taking a test. But this is one, I took a Calculus 2 course with Arizona State. I don't think I ever had to know this formula. I think for one of the tests, I had it. I had it figured out in my brain if I needed it. But anyway, it's one that if you have a little extra time on your hands, I've got, 60 minutes to kill. Hi, why don't I memorize that the derivative of secant theta is secant theta tangent theta? All right, so anyway, we don't have, I'm telling you that's what it is, so you don't have to look it up right now. So we're going to substitute in a secant of theta for the x. Very important, however, we've got to substitute in a secant theta tangent theta for dx. That's something I've sometimes missed in the past. Always remember to substitute in the dx part as well. So that looks awful, but the bigger they are, the harder they fall sometimes. So we've substituted in a secant of theta for x, which becomes a squared secant squared theta. A squared stays the same. And then we've substituted in for dx a secant of theta tangent of theta. By the way, again, the a is a constant, so it just comes right over. And the derivative of secant theta is secant theta tangent theta. All right, so there we go. We got this monstrosity here, but not for long. It's gonna work out. I think it's gonna work out. So first of all, we can factor out the square root of a squared is a. So plop, there we've got an a. Already things are beginning to cancel. So the a's are going to cancel. What about this secant theta minus 1? There is a formula you should know. I think that could it be, pull it forward, could it be, yes, the secant squared theta minus 1 is the tangent squared theta. That's a thing you should know. Alternatively, secant squared theta equals tangent squared theta plus 1. Again, that's one where you don't have to have them both memorized. You just need to have one memorized and then use algebra as needed for the other one. Well, this is good because we know that tangent squared, the square root of the tangent squared theta is just tangent theta. And then these are going to cancel out, isn't it? Lovely. So the a's cancel out, the tangent thetas cancel out, and we're left with the integral of the secant of theta. This is another one that is on the tip of my brain. Sometimes I remember it, sometimes I don't. But it is, you know, if you're gonna go the long distance with math or engineering, you should probably just memorize it. What is the integral of the secant theta? It is the natural logarithm of the secant x plus tangent x plus a constant. And there you have the answer, right there. By the way, I don't know if it helps you, but one thing that keeps it on the tip of my brain is it seems like that whether you're taking the derivative of secant theta or you're integrating secant theta, it adds a tangent, right? So here, when I'm doing the integral of the secant theta, it adds a tangent. Now, you have to remember the natural logarithm part. It's the natural logarithm of the absolute value of secant x plus tangent x, right? But even back here, when we were doing the derivative of it, it added a tangent. Now, it added it in a different way. But I don't know if that helps you, but I kind of have on the tip of my brain that when I'm either taking the derivative of secant theta or I'm doing the integral of secant theta, it adds a tangent. Who knew? So derivative of secant theta tangent theta, and here, on the next page, blah, 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 come on, get it, there we are. The integral of secant theta is the natural logarithm of secant plus tangent. Well, have I beaten the dead horse enough? There you have it. Substitute, when you have the square root of x squared minus a squared, substitute in a secant theta. I lied. That's not our video. It still goes on. We've got to get it out of this trigonometric form back into a purely x form. I'm so sorry. And the way we're going to do this is we're going to do it by using the triangle, the triangle, picturing the triangle again. All right. So remember when we started down this rabbit hole, we made x equal to a secant theta. Now what that means is that if we divide both sides by a, secant theta equals x over a. That m is a mistake. M for mistake. Imagine that. So the secant of theta equals x over a. Ignore the m. So if we flip it, that's the same as the cosine of theta being a over x, because what is secant? It's 1 over cosine. So if cosine, if I flip it, is a over x. Now I can use this triangle to figure out. So if x is the hypotenuse, then the cosine of this, if this is theta, the cosine is the adjacent over the hypotenuse, a over x. So the cosine of theta is a over x, right? So what is a squared plus b squared equals c squared? What then would be the opposite side if I did that? Well, a squared plus x squared a squared plus whatever squared equals x squared. So if I get the a over to the x side, I'm left with whatever this side is equals whatever this side is squared equals x squared minus a squared. Take the square root is, then whatever this side is the square root of x squared minus a squared. I didn't write it down, I'm sorry, but you could do it. It's the Pythagorean theorem, solving for this side, and this is what it comes up with. And by the way, as I've said, a lot of times when you do these, you end up going back to the original problem, whatever you substituted ends up being, the side when you're plugging it back in. So what this means is that I've substituted in for secant x over a, and I substitute in for tangent the opposite over the adjacent, Now we've gone back and we've put it into the form that we started with. So here's the formula, and you'll find this if you go to the back of the calculus textbook, that the integral of dx over the square root of x squared minus a squared, that's the problem we started with, equals the natural logarithm of the absolute value of x over a plus the square root of x squared minus a squared over a plus c. And so now, are we done? Well, okay. If we go ahead and wrap the a into the constant, so multiply through by a, the constant just will absorb that a, so we can put the formula finally in this. This is what you'll find in the back of the textbook. Natural logarithm of x plus the square root of x squared minus a squared plus a constant. That is the answer to our problem. This time I'm really done, I promise.